morning this time. We changed locations, so I'd like to start as usual with my acknowledgements to morning this time. We changed locations, so I'd like to start as usual with my acknowledgements to Maria Barraza in the math department for the technical support, and Marta Delgado for sponsoring this series on calculus under the umbrella of Marx. So we'll discover a few things here in terms of trigonometric or circular functions and hyperbolic functions. And for that, we'll have to bring some prior knowledge associated with it. So I'll start in this fashion. The circular and hyperbolic functions. Okay, so circular as they are defined on a unit circle, hyperbolic as they are defined on the unit hyperbola. But to start with this, let me initiate with the following configuration, which is the one that we're most accustomed to. So if I start with a unit circle on a coordinated XY plane, we know that it satisfies the equation x squared plus y squared equal to 1. Then we indicate, well, how do we define the circular functions here? Well, we take the origin, right? Then we drop a line. Then we take a measure, right? And we presume that this is the positive direction, right? If we were to measure in this direction, that would be negative. But what is indication here? Since we're working on the unit circle, right? There's a direct association between the angle that we describe here in radians and the length that we have, say, sine length, now that we're making this observation. In other words, we can capture and define the point of intersection, the unique point of intersection with the unit circle in terms of cosine of that angle. That's how we define it, especially. So we would declare that cosine of theta is the first coordinate of the unique point of intersection of the line segment, of the first coordinate of the unique point of intersection of the line segment that crosses the origin at an angle theta. Well, where theta is interpreted really as a length on a unit circle, right? As a real number. If we measure in this direction, it becomes length. So with this in mind, now we have the following tools, right? So we see that cosine of theta and sine theta are defined as coordinates, of course, first and second respectively. And now we can investigate the properties of these functions in terms of its input, right? Differentiability, integrability, things like that. So the first one that I really want to explore is that associated with the derivative of sine. We're going to demonstrate in a second just by showing that actually sine is differentiable and cosine is differentiable, and at the same time indicate that the functions that we're defining here are indeed what we would say continuous as well. So what were the limitations associated with this one? Let's see. As we start a series of computations, recall that a function is differentiable at a certain value x equal to a function, of course, of x, just to give it a name, whenever the following occurs, whenever the limit as h tends to 0 of f of x plus h minus f of x divided by h. And here I'm stating that I'm differentiating at a, saying that this exists and it's finite. Be precise. Okay, so let me start with this observation. Let's see what are the limitations or the indications that we have to associate when we calculate the derivative of cosine, if it's possible. So I want to investigate the limit as h tends to 0 of cosine of x plus h minus cosine of x over h. That's the first thing that I want to do. Okay. But let's see. For this, I think that we need to recall a few things from the past, because now we are investigating two things: the limit as h tends to 0 of this expression, which is associated with the derivative, of course, and the one that is the limit as h tends to 0 of sine of x plus h minus sine of x over h. And then we will say, well, look, there's really not much that I can do with this expression. However, I think we can bring some prior knowledge about the sum of angles for sine and cosine. So, from recalculus, we can indicate this. Recall that sine of alpha plus beta and cosine of alpha plus beta, well, these two are given in terms of sine and cosine of the angles that we have here. So, for instance, cosine is expressible as cosine of alpha times cosine of beta minus sine of alpha times sine of beta, while sine may be expressed as cosine of alpha times sine of beta plus cosine of beta times sine, sorry. Yeah, just exchanging those two. So those are the sum of angle formulas that we learned from trigonometry. And let's see if we can apply them here and still being able to provide at least some indication of what are the things that we need in order to calculate these limits, right? So let's see. Let's work out with this expression. Again, I'm saying nothing about the existence of the limit of this fraction. All that I want to do is to explore what are the things that I need. So if I start with this, let's say sine of x plus h minus sine of x. Well, immediately from here, I say, look, the expression that I have here might be just decomposed now in the following order. I would say cosine of x times sine of h plus cosine of x times cosine of h times sine of x, all divided by h. And then I see, look, It seems at this stage that we need to gain information about the following. Look, if I was to rewrite it, I have cosine of x times the sine of h over h plus cosine of h over h times sine of x. In other words, in order to gain information about this limit, we may explore these two limits, right, that we have here. Right? I mean, the limit as h tends to 0 of these two. So let's investigate that one. And for that, I'm going to use the unit circle that we used to define the sine and cosine functions. So I'm going to erase this picture, as I have to include a little bit more things. And I'll do it in just a second. So I'll start in this fashion. Now, I'm going to drop an angle. I'm going to call it h. So in this case, h, it's going to be positive. This is the unit circle, just as before, because I want to investigate this expression, sine of h and cosine of h. So based on this, I'm going to drop a tangent. I know that the tangent to a circle forms a 90-degree angle with its radius, with one of the radius associated with the point of intersection. And from here, I'm going to extend a couple of things. I'm going to extend the triangle, right? All the way up to here. And then I'm going to consider three elements. The first one is the one that we have associated with this triangle. So we examine the triangle. Well, of course, we know the coordinates of this thing, of this point. They're actually by definition cosine of h, sine of h. Then you would say, well, wait a second. Would it be possible, well, to label the side of this right triangle? This is a height. Of course, you can say that this is cosine of h, while this one is sine of h. But then you say, look, let me make a comparison. I'm going to build another triangle. Now the one that we make with this tangent. So I expand this one, and now I say, well, what should be the length of that side of that right triangle? Well, look, this is a radius, so the unit circle, so it should be 1. And then we say, well, but what about the height of that? Okay. Well, that's not really a complicated story, because for this, we can use tangent, right? Look, if I have, there's a relation between tangent of h and these two sides. In fact, tangent of h would be, well, the opposite side divided by the adjacent side. Well, that would be exactly, well, this height divided by 1. That indicates that this length must be tangent. Tangent of h. Let's see. So what would be the indication here? Well, let's see. I think, look, even though I have labeled all those things, then I can impose an additional relation. I observed that the area defined by this triangle, which is associated with cosine and sine, and the area associated with the big triangle, associated with this one in tangent, well, they are ordered. The area of this triangle that we have here is smaller than the area of the triangle that we defined just right here. But not only that, there's another relation which is the one that is given by the sector. So here we have three pictures in place. We have the triangle, angle H, side cosine of H, height sine of H. We have a sector on the unit circle, angle H, radius 1, radius 1. And we have another triangle, a little bigger, with angle H, side 1, height, tangent of H. And I'm going to use parentheses just to indicate that we think of this as a function. Notice a different. Okay, then we'll make a comparison. I'll take the area. The area of this triangle, right, is smaller than the area of this sector, which in turn is smaller than the area of the big triangle. So that puts me in a position where I can make a comparison, but now turn this geometric configuration and write it algebraically. So if I say, if H is positive, and in fact is on the first quadrant, meaning that H is comprehended between, well, I'm gonna avoid that portion, H and let's say less than, let's say pi over 2, just to be working strictly here in the first quadrant. Then I have the following. The area of this, which would be sine of H over, I'm sorry, not over, but sine of H, base times height, so cosine of H times sine of H divided by 2 is less than or equal than the area of the sector defined here, but the sector, well, actually, what should that be? Well, let's not forget we're on the unit circle, so the length that we have associated here, the arc length, is exactly the number of H. If we measure H in radians. So, and that's the importance of measuring in radians because there's a nice correspondence between the arc length on the unit circle. So, what will be the area associated with this? Well, in fact, the area of the sector that we define here is just a portion of the entire circle, or the area bounded by the entire circle. But how much of it? Well, H over 2 of it. Which in turn, you can say, well, same thing about a triangle. Height times base divided by 2. So 1 times tangent of H divided by 2. Immediately from here, we obtain the following. We would say, well, multiply everywhere by 2, and you get cosine of H times sine of H is less than or equal than H, which is less than or equal than tangent of H. But then from here, I'm going to recover tangent as what it is. Tangent is nothing else but sine of H divided by cosine of H, right? Where we call the definition of tangent as a trigonometric function. But then just from here, I look at the following. Well, let's see. There seems to be a lot involved, but remember what we want to obtain. We want to obtain a relation about sine of H over H. Right? We want to investigate that fraction and see what happens as H tends to 0. Well, I think at this point, one thing that I can do is simply start dividing. And what is that I'm going to do? Well, look at H. I'm going to multiply everywhere by 1 over H. Well, should I do that? Not necessarily. Yeah. Let's see. Let's massage. Let's manipulate the above relation. I think for a second. Since we are defining sine, well, we're defining h restricted to this set of numbers. I know that on that interval, sine has to be positive. So why don't I do one thing just at once? I'm going to multiply not by h, but multiply by the reciprocal of sine. That way, essentially, we'll get rid of this one and we'll get rid of this one. So since this is a positive number, we're working here, let's not forget about that. And it's important that we don't touch 0 and we don't touch pi over 2. Recall it, it should be less than or equal than 1 over sine of h, which in turn will be less than or equal than 1 over sine of h times sine of h divided by cosine of h. Then right after that, I can say the following. Look, this would cancel. This would cancel. And this expression simplifies to cosine of h is less than or equal than 1 than h over sine of h, which in turn is less than or equal than 1 over cosine of h. Then you would say, well, look, since we're working here, this quantity is different from 0, this quantity is different from 0, and this quantity is also different from 0. So, well, taking reciprocals would exchange this expression, right? Meaning that we will get something that looks like this. So 1 over cosine of h, it's greater or equal than sine of h over h, which is greater or equal than cosine of h. And then from this point, look, what I'm going to do, since h is restricted to this domain, I'm going to send h to 0 from the positive side. And from that, well, look, what happens to cosine as its input goes closer and closer to 0? Well, it will get closer and closer to the cosine of 0 by the continuity of h, of cosine. So that would indicate that the limit as h tends to 0 from the right of 1 over cosine of h, including sandwich theorem, would be less than or equal, greater or equal than the limit as h tends to 0 from the right of sine of h over h, which will be greater or equal than the limit as h tends to 0 of cosine of h, of course, from the right. Then you would say, well, just from this observation, what I see is that, of course, this limit is computable. This is 1. This limit, I have no idea what it is. So just write it in the way that it's just written. And this one, well, it evaluates to the cosine of 0, which is just. So that means that this number, well, whatever it is that is tending to, is comprehended between 1 and 1. So the limit is 1. That means that this expression that we have here tends to 1 as h tends to 0 from the right. Now, a similar procedure may be utilized to demonstrate that, in fact, it tends also to 1 on the left, right? As h approaches to 0 from the left, taking negative numbers. So you can simply take that one. That goes to 1. But what about this one? Remember, coming back to the expression involving the derivatives, what should be this? Well, it's not so much of a surprise that that quantity is slightly different. It should tend to the following. Let me just erase this portion. We would say, well, let's make an exploration about this. Here, before I forget, I'm only exploring this portion, but there's an equality that is missing here because I should be saying minus sine of x. So here I should be saying also minus sine of x. We do this all over here so that becomes a little easier to handle. Okay, so there's a remaining question of what is it this is tending to. So let's wait a second. So now all that we have to do is to accommodate a few things. Let's see. We have the limit as h tends to 0, right? Of the expression sine of x plus h minus sine of x over h. Well, that one is the limit as h tends to 0. Let's do some algebra here of cosine of x times sine of h plus cosine of h times sine of x minus sine of x, all divided by h. Now let's wait a second, because from here I'm going to make the following expression. I'm going to rewrite this algebraically. So this is the same as the limit as h tends to 0 of cosine. In this case, what I'm going to do is associate in this fashion. So I have cosine of x times sine of h over h plus, now look, the expression that I have here has in common a sine. And having in common a sine, it means that I can do the following, I can factor. So I have cosine of h minus 1 over h times sine of x. Then you would say, well, what happens with this? This one is well known. That one tends to 1. But what about this? Do we know where that tends to? Well, let's see. Let's explore this quantity. I know I'm spending a little bit of time on this derivatives because at some point I'm going to just immediately talk about integrals in a second. So what I have here is the following. I have cosine of h minus 1 over h. And I want to investigate what is the limit of this expression as h tends to 0. Well, look, here we have a difference. Immediately, once you have a difference, you would like to introduce a couple of things. The first one that I would like to say is the one that is associated with this. This is sine, not sine, sorry, but cosine of h plus 1 over, by introducing a conjugate. Whenever I do this, then I have cosine of h squared minus 1 squared over h times cosine of h plus 1. Then from here, well, look, there's a fundamental identity that relates cosine and sine, which is the one that we had from the unit circle, that indicates that cosine square of whatever we have in terms of angles plus sine square of whatever we have in terms of angles, well, that difference can be manipulated into something that looks like this. So this is in fact nothing else but negative sine squared. So I'm going to introduce it in that fashion. This is negative sine squared of h divided by h times cosine of h plus 1. Then you say, well, look, But I can decompose this square as actually what it is. It's factors, so I'm going to multiply them both. So I have on one part sine of h over h times, using properties of fractions, negative sine of h over cosine of h plus 1. Then look, I managed to re-express this fraction as a product of these two fractions. Of course, there are certain restrictions, right? But we can sort them out. And we ask ourselves, well, what happens to this quantity as h tends to 0? Well, this one tends to 1, as we just demonstrated. But this one, well, by the definition that we provided in terms of length, it's possible to demonstrate that sine and cosine are continuous functions. And I should be careful with the things that I said at the beginning, because I mentioned that we wanted to demonstrate the continuity by the differentiability of these functions. But no, we have to take into consideration that the functions themselves are continuous in order to even talk about the differentiability in this case. If we were to use a different definition, then we would be able to do it, but that's not what we're doing here. Just as a caveat and a correction of something that I just said. Okay, so from here, I would say, well, look at this expression that we have here. Being continuous, it tends to sine of 0. Negative sine of 0 over, well, cosine of 0 plus 1. But this is nothing else but 1 times 0 over 2, which is just 0. So it goes to 0. This one goes to 1. This one goes to 0. But we look at the expression, right, as we just broke it down. We know from these calculations that goes. So what do we learn from this computation and all this work? Well, that indeed the derivative of sine is cosine. But I have to express it here, provided that continuity of cosine and sine, we get that the derivative with respect to x of sine of x is cosine. And in fact, it doesn't take too much work with the things that we have done to demonstrate that the derivative with respect to x of cosine of x is nothing else negative sine. And then just from this observation that we have here, I mean, I'm just taking, I have to be a little bit faster, but it's essentially the same type of computation and essentially the same type of derivation that will allow us to demonstrate that the derivative of cosine is just negative sine. But what does this mean in terms of the derivatives? Well, look, if I was to take another derivative, let's say now in terms of sine, let's say that I have a sequence. Let's start with sine of x. It's a function that is defined on the entire real line. And then from here, I'll take the derivative operator with respect to x. Well, that will give me the cosine. Right? But then if I take another derivative, that would say derivative with respect to x of this expression, meaning the second derivative of that one, that will give me the negative sine of this. And then you say, well, what if I take the derivative of that? From that one, the x one more time, that would be, look, the derivative of, this is just the negative of that one, which is just a scalar product of this one. Well, that should be negative cosine of x. And then what if I take another derivative? Well, if I take another derivative, same thing, I will be just coming back to that. So it's effectively constructing a circle here. If you like to see it in that fashion, it's just a cycle. It becomes cyclic. And actually, it doesn't matter where we start. Maybe just to make it nicer, we put it here. it doesn't matter where you start. You can say sine of x at 12 p.m. Then cosine of x at 3. Then negative sine of x at 6. Then negative cosine of x at 9. If we indicate that the arrows represent taking derivatives with respect to x, we obtain that cyclic behavior. And it really doesn't matter where you start in that circle. You can circulate around this ones. What does that mean in terms of the derivatives of these things? Well, first thing, note that the second derivative of sine is it's negative. What can we say about cosine? Exactly the same thing. So in other words, we can say that the functions that we have here satisfy the following equation. Differential equation. What is a differential equation? It's an equation that relates a function with its derivatives. So if I start with a function and derive it twice, then I add it, and I get 0, well, I see that sine and cosine satisfy that. Now, in fact, this is a fundamental equation that defines fundamental differential equations for which we can think in terms of sine and cosine. Then you say, okay, what else do we learn from this app? Well, not only in terms of differential equations, but also in terms of antiderivatives. Because what is it we learned just from this diagram? Well, what happens if I reverse it? Well, if you reverse it, look, what we have is this. In some sense, we think, of course, which is just an intuition. We think of integration or anti-derivation as exactly that, doing the inverse process or the inverse operator to take in derivatives. Of course, that has to be taken with care because an integral is supposed to initially represent information about the area. But it's not a big surprise that now I can indicate things like this, that the antiderivative of this function, the sine, should be negative cosine, constant. And also that the antiderivative or the indefinite integral of cosine of x dx must be all the functions that satisfy the properties that differ with sine with by a constant. So you may say, well, if this is actually the case, right? And the presentation that we had here was about circles at the beginning, right? But you mentioned something, you said, well, you can argue, say, well, at some point you said something about hyperbolic functions. I said, well, of course, but where are they appearing? Well, that requires an additional work, but I want you to keep this part in mind. This differential equation. There's a slightly different definition for the circular functions. Slightly different in terms of now not using the length, but the area to define it. So if you take a circle, unit circle, center at the origin, Then you drop a line emanating from the origin, right? You record the first and second coordinate of this point of intersection. Then, of course, you drop an angle, which we know is associated with the length. It's going to be the same as, well, the one that we write here, right? As we measured in this direction. Well, one question that we can ask ourselves is, what is the area of this object, right? We're defining here. Now, as we just mentioned it, the area is nothing else but x over 2 when x is measured in radians. And we may define cosine exactly in those terms. We may define cosine as the unique number for which the area is exactly x over 2 under this construction. What would be the sign? Well, it's the one that respects the original circular definition. So you would say that once you define cosine, well, sine of x would be that. So you would start by saying, I want cosine to be the unique number for which this happens, and I want sine to be exactly just this, so that it actually satisfies this expression. Well, good for the unit circle. But what about the unit hyperbola? For the unit hyperbola, we have the following expression. We have the following picture. To be more precise. This one represents x squared plus y squared equal to 1, unit circle. What about that one? Hyperbola. Unit hyperbola. Pardon my writing my figures here and representation of the object that I'm trying to describe. Have an origin, just as I had before. But now, kind of in the same fashion, look at the origin, and then I drop a line, forming an angle in this sense. Has to intersect the parabola at some point. Then you say, well, I'm going to measure the area. Essentially, the same fashion. And then I record a coordinate. First and second. Well, the area for which this sector, what we call the hyperbolic sector, is x over 2. That one corresponds to the hyperbolic cosine. What would be this one? Well, by naming conventions, hyperbolic sine. But we should not forget that it comes from a definition associated with the angle, with the area associated with this sector. You measure that. When you measure and you say, now the angle, the area is x over 2. Once you arrive to that point, you measure this one, then you look at the first coordinate, that's what we call cosine. You look at the second coordinate, that's what we call sine. Hyperbolic in both cases. Just as we say, well, when you look at a circle, you measure the angle, you measure the area in this fashion until you get x over 2, and then you say, boom, okay, I'm stopping at x over 2, I record this one, I record that one, this one is cosine, this one is. That's by definition. But just by looking at this, well, what should be the equations that this thing should satisfy? Well, it better be that it satisfies this, because it's a point of the hyperbola. So immediately we get the first identity. Of course, this may require additional work, but we can demonstrate that we should be able to parameterize it using exponential functions. And in this fashion. In fact, you may even take it as a definition and just take it from there and then happily turn out to be that indeed it measures exactly the same thing. But you can take this as a definition if you like it to. Now that we have defined logarithms and exponential functions, you may define sensibly that the cosine hyperbolic of a number is nothing else but e to the x plus e to the negative x over 2. And then from this observation, you can get that the hyperbolic sign is nothing else. And then you start making explorations. You say, what if I take derivatives? Well, but something that we learn about the exponential function is that the derivative of the exponential function is itself. So if we start saying, right, with respect to x of cosine of hx, that would be, let's see, this is the derivative with respect to x of e to the x plus e to the negative x over 2, which is just, well, taking fractions. That would be 1 over 2, derivative with respect to x of e to the x plus e, well, to the negative x, just like that. The basic fortune is make it clearer, e to the x plus e to the negative x. Chain rule will have e to the x minus e to the negative x. That's exactly the hyperbolic sign. What if I take another derivative? Not to be confused with the sign of h. This is a different hyperbolic sign. So if I take the derivative of hyperbolic sign, what do I get? Well, sine is this definition. So the derivative with respect to x of this expression, and that would be what? 1/2 of e to the x minus e to the negative x. And then you would say, well, look, we have, this is nothing else but 1/2 of e to the x plus e to the negative x, which is nothing else but the hyperbolic cosine. So with sine, with the trigonometric functions, we have a cycle of 4 in terms of derivatives. But with the hyperbolic functions, we have a cycle of 2 in terms of derivatives. So essentially, we have this picture. We would say, look, starting with cosine, now this time, cosine hx, you will get sine hx. Then taking derivatives again. That means that if you take the second derivative of the function, you get back to itself. But we may express that as a differential equation. The second derivative minus the function of h to c. Of course, once you indicate some specific conditions, you will recover this, that one, as you please. As if you start with these conditions and you impose additional, if you start with this equation and impose some conditions, you will recover cosine and sine. So you can take any of this 3 different versions to define the object that you're talking about. You may try to parameterize a parabola, as actually we can demonstrate that indeed, if you start only with these definitions, they indeed parameterize a parabola. As if you start with the trigonometric functions as we define them, it will parameterize a circle. Or you may say, no, look, I want to find functions that satisfy this particular differential equation or this particular differential equation. Well, the ones that look like this one, they will be associated with the hyperbolics. Well, these ones will be associated with the circulars. So then we would say, aren't the equations looking very similar? They do. But for that, well, take differential equations, no, because that is a theme for a different type. Now, something that I want to mention just before we finish with the exposition for today is what happens with the inverse of these things. Well, to study the inverse, I would say I really want to have those two at the same part of the board. But how do we study the inverse to a function? Well, by a fundamental relation, which is, for example, if we look at sine, not define on its entire domain, because otherwise the inverse would not exist, right? But only on the interval from negative pi over 2 to pi over 2. Well, if we do that, this is y equal to sine of x, as we plot it. Well, we see that the function here is increasing, being increasing and differentiable. It should have it's 1 to 1, so it's 1 to 1 on its domain. That means that if we look at the inverse relation, that inverse relation has this. It has an inverse. And what would be the range of that one? Well, exactly. We plot them here by continuity considerations. It should be -1 and it should be 1. So it touches every single element from the range, from the interval from -1 to 1 inclusively. So we just take sine x to be that. Well, what would be the inverse? The inverse essentially just reverses the arrow of application of function. And we define arc sine of x to be the inverse of that. Is in this fashion. But then you say, well, why is that you're choosing this name in particular? And why is that you can use a single name? Well, I can use a single name because the inverse is unique. There's only one. But then you can also say, look, if I was to compose them in this fashion, sine of arc sine of x, the inverse, and I'm not saying say sine to the -1 because that is really troublesome. That makes a confusion with the reciprocal of sine. So why don't we give it a name? Names are bound. It satisfies this, of course, only where this makes sense, right? When we're composing. But if we use this equation, then we can say, well, take derivatives everywhere. You say the derivative with respect to x of this expression, sine of arc sine x, is equal to the derivative with respect to x of x. The same trick that we're going to develop here applies for every single invertible function. So, chain rule, it says, whatever I have is cosine of the arc sine of x times, I'm going to use the notation dx of arc sine of x is equal to 1. So just from here, you can say, well, look at this expression. What is that this is supposed to be? Well, something of this fashion. I have the derivative with respect to x of arc sine of x is equal to 1 over cosine of arc sine of x. Then you may say, well, that one looks that doesn't really look like something that we have seen. Well, let's not forget what these things measure. You provide a number, this one provides an angle. So let's give it a name. We call that angle theta. And I'm going to restrict myself to positive angles on the first quadrant, but the same argument may work elsewhere as needed. I have this as theta. So you need to make a construction. Well, what is this saying? Well, I'm saying that theta is the arc sine of x. But what is this saying? This is the equivalent as to indicate that the sine of x, I'm sorry, the sine of theta is equal to x. So what I'm going to do is construct a triangle with the appropriate information. Well, I can write this as x over 1. Sine is opposite over hypotenuse, so I have x. Well, this one is 1. And this one, well, I just take a measure, Pythagorean theorem, that should be 1 minus x. So the cosine of theta is adjacent over hypotenuse. That means that this is now look, we actually gain access to the following. The indefinite integral of an expression of this form. Same game can be applied to not only the arc cosine, the arc tangent, the arc cotangent, the arc cosecant, the arc secant, but to the arc hyperbolic tangent, the arc hyperbolic sine, in order to gain information about their inverses. And with that, we will get access to integrals of this form to which we had no idea how to calculate before. So, I look forward to seeing you next time with further computations and further elementary integrals. Take care.